And on the shampoo, it shows this one. Okay.
Does it does it tell you which contact is it referring to? Between which two parts?
It's on the screen.
Okay. I would go ahead and try running it first. And
It does give the result.
I'll give the result. Okay.
Yeah,
Okay.
this shows-
Yeah, some warnings you can ignore it.
Okay.
Are all your supports bonded supports or some non-bonded?
I'll check.
Okay.
Yeah.
If it's not, try making all of them bonded first, because
Okay.
that's usually the most stable, and see if you get the same warning. But if it's all bonded already, then and it's running, then I think it's okay. But yeah, if you run into issues, just let me know. Send me an email.
Sure.
Yeah. All right, it's 5:30, so let's go ahead and get started. All right, good evening, everyone. How's everyone doing? Did everyone have a good break, hopefully? Yeah, good. I saw some family members over the Thanksgiving break that I haven't seen for like literal years because of the pandemic. Literally, I went to one of my uncles for Thanksgiving, and my cousin opened the door, and I remember that cousin because I used to look at him like this. Like now I'm looking at him like this in the 2 years that went by. Like, it's crazy. Like he opened the door and like he has much better fashion sense now. So he opened it. I'm like, man, who the fuck are you? I'm like, oh, you're Ethan. Like, wow, you grew a lot, man. But yeah, that's what the pandemic does to people, I guess. Okay, and so we're on our last 2 weeks, and so it's very quickly getting to be the end of the semester. And so the plan for the rest of the semester is this week we have another ANSYS activity planned, right? And so it's our last one, and it's on a fairly, in a grand manner of speaking, compared to all the other activities that we did. This is, I think, is a fairly minor topic. It's kind of a niche. It's a pretty niche feature. That's not to say it's not useful, and so it's definitely a useful one for certain kind of structures. But I would say as a field, there's not really as much to talk about in compared to like dynamics or modal analysis. But it is an important feature of ANSYS, and I thought it'd be a nice fitting feature to end with because it is fairly simple. Just so that you guys can spend more time on your final projects. Okay. And then next week will be a kind of like I'll let you guys choose kind of what we cover because I have quite a few handouts that I've developed over the years for ANSYS on kind of other niche features that are there. And I'll let you guys vote on what you want to see. So I have handouts on things like thermal simulations. I have a handout on fluid simulations, so CFD. I have a handout on anisotropic materials. I have one for fatigue testing. I might have one or two more that I'm not thinking of, but we might have time to cover all of them just because each one is only about half a lecture's worth of content. But I'll cover them in an order that you guys will have. Okay, but this is kind of the last week of kind of really required stuff, and then next week we'll do kind of more more miscellaneous topics. Question: do I have anything on additive manufacturing? I do not, actually. So that's definitely not an area of expertise for me, and so I don't have anything prepared for that. Yeah, unfortunately. But if it is an interest area, and unfortunately, I don't think I'll have time to prepare anything in time for this class. But maybe it's something I can develop for future classes. And if you're interested, then whenever I do develop something like that, I can send it over your way too. Okay. All right. And so today, we have a lecture where we're going to go over buckling stuff, and then Wednesday we're actually going to put it in practice. Okay. All right, and then due dates. And so there are 2 activities that are still left to be due, and so activity 7, I believe, is due this Friday, which is the 3rd of December, and then the buckling assignment. I don't anticipate it being that long of an assignment. I'm hoping that everyone can probably actually finish it up on Wednesday. I'll have that due next Friday, which is December 10th. And then after that, the last thing that's due will be the final report, or remember that's due on December 20th. Okay. All right. And so I think that's all my announcements. And so are there any questions I can answer before we get started?
The templates for the final.
Oh, the template. Yes. I'm sorry. Yeah, I keep forgetting about that. Let me do that tomorrow, and I'll put that up. Thanks for reminding me. Yeah. Okay. All right. So let's go ahead and get started. So let's talk about buckling and the stress stiffening effect. All right. And so let's start by just kind of reminding ourselves that one of the primary objectives of a structural FEA is to determine whether a structure will fail under given loads. Okay. Okay. And, the way that we usually check this is, after we ran our simulation, we would look at the equivalent stress field, and we would check to see if the equivalent stress, if that exceeded the yield strength of the material. Okay. All right. And so with that note, most of the time, for most of the activities that we've gone over this semester, most of the time when we say that the maximum equivalent stress exceeds the yield strength, that's usually some kind of tensile stress. Okay. Okay. And the reason for that is, if you look at a typical material, usually its tensile strength is going to be lower than its compressive strength, right? So a lot of materials, some materials, they don't differentiate, but for other materials, if you look at, their different yield strengths, you'll see that the tensile strength is low. And so, what the kind of general inclination is to say is that, this structure will fail faster in tension than it will in compression. Okay. Okay. And so, in the grand scheme of things, we haven't really looked at compression all that much. Okay. But compression loads are really important, right? Maybe not in the ways that we've been thinking before, but compressive loading causes a very unique phenomenon to occur called buckling. Right? And buckling is a very unique phenomenon in structures. And when someone says a structure is buckling, it's what's really happening is that as you apply more and more compressive stresses or more and more compressive forces to a material, you're actually affecting the strength of that material itself. Okay. And in particular, the strength that goes down is the material's resistance to bending stresses. Okay. And so as you apply more and more compressive forces, it becomes easier and easier for you to bend that material. Okay. And once you reach a certain point, then it can cause the material to go under some very drastic kind of deformations. Okay. All right. Any questions on this? Okay. All right, and so when you see buckling occurring, usually it's very dramatic usually, because it almost seems like the material itself kind of collapses on itself, and that I think that's kind of the best word that I can use to describe it. Okay. Okay. And I think probably the example that most people are familiar with is smashing a soda can. Or this work even works with the water bottle too, right? And so if you have a can of soda, right? Okay. Right. What a lot of people like to do, and actually, it's becoming more and more common practice because it saves a lot of space, and I mean, ideally, these get recycled, but a lot of them actually end up in the ocean, unfortunately, right? So in order to save space on these, what people like to do is they like to smash them together, right? And so they apply a force like this, right? And so maybe they put the can on the ground and then they stomp on them with their foot, okay? And so you have basically forces that apply like that. So you have a very large compressive force, okay? And and what you'll notice, right, is that once you apply this compressive force, the can doesn't just deform slowly. It deforms kind of all at once very quickly, and it's a very violent kind of satisfying process to undergo, right? And so in the end, the soda can might look something like this, right? Right? Where the edges are all kind of like sprinkled and wrinkled up like that, right? And right, the name might be like that. Maybe that's not realistic, but but in other words, you get this kind of appearance, right? And in particular, what I want to draw your guys' attention to is the shapes of the sides, right? Because what did we say on the last page, right? And so on the last page, what we said is, when you apply a compressive force to material, its resistance to bending forces or bending moments lowers dramatically, okay? And so the reason it has this kind of scraggly appearance right here is because, as we apply the compressive force on the can, then the walls of the can, their resistance to bending went down. Okay, and so that's why you have these kind of wavy, almost wavy patterns on them. Okay. Okay. Because what's happening, right? And so as we're applying our compressive forces, then then the size of the can, in order to kind of maintain conservation of mass, it'll start to kind of wrinkles and ripples will start to form on the side of the can, right? And so in other words, the sides of the can will start to bend, right? And so as it starts to bend like this, okay, right? But as we apply more and more forces, the resistance to that bending is going to go down and down, right? And so if you only apply a very light amount of forces, you might see the side of the can start to kind of bend like this, right? But its bending stiffness is enough so that when you remove the forces, it'll go back to kind of a straight side like that, okay? But once the compressive forces get to a certain amount or a certain threshold, then it can't resist bending anymore. And then just kind of all of a sudden violently, the bending just kind of gets out of control. And all of these kind of ripples on the surface just kind of go outwards, just like that. Okay. And you end up with, the situation like here on the right. Okay. All right. And so that's kind of buckling in a nutshell, right? And when we analyze buckling from a finite element point of view, we're interested in this kind of situation here, where what we say is we have kind of catastrophic buckling failure. We're kind of all of a sudden, the compressive forces reach a point where, the whole structure just kind of violently just kind of falls apart. Okay. Okay. And the point of buckling failure, actually has a formal definition. Okay. And so the point of buckling failure is when the compressive forces that we apply are large enough such that the bending stiffness goes down to 0. Okay. Because when the structure can no longer resist any kind of bending moments, then that's when you get kind of this soda can catastrophic failure kind of stuff. Okay. And the eigenvalue buckling module in ANSYS is kind of perfectly designed to help us determine this. Okay. All right. Any questions on this? Okay. All right, and so what's really going on under the surface, right? And so we've kind of described what buckling is kind of visually, and kind of what to look out for. But kind of the formal name for it, in structural mechanics, is known as the stress stiffening effect. Okay. Okay. Right, and so the stress stiffening effect basically states that as structures are exposed to tensile and compressive forces, then its resistance to bending or its bending stiffness will change. Okay. In particular, we've seen that when we have compressive forces, the bending stiffness will go down. But actually the opposite is true as well. And so if you expose a structure to tensile forces, its bending stiffness will actually go up. Okay. Right. So overall, both of these effects combined is the stress stiffening effect, right? And kind of the special case of the first one here, where you apply enough compressive forces such that the bending stiffness goes to 0, that's what's known as buckling. Okay. All right. So just to kind of state this formally, if we take this case here, And so when the bending stiffness goes down to 0, this is what's known as buckling. Right. And so what's interesting about buckling is that, if you compare the point of buckling, right? So the compressive forces that cause buckling, this is usually a lot less than the compressive yield strength of the material. And so what you'll see most often is that a structure will buckle way before it actually fails in compression. Okay. Okay. Right. And so that's why it's really important to determine, because if you simply look at just the compressive yield strength of the material, then you might be kind of given a false sense of security that your structure is safe. But if you don't look at buckling, you might be ignoring a very very important and very catastrophic failure. Okay. All right. And so what we're going to do on Wednesday is we're going to basically learn how to set this up in ANSYS and determine whether a structure will buckle using a specialized module called Eigenvalue buckling. Okay. All right. Any questions on this? Okay. All right. So let's do. It's an example, but we're not actually doing any calculations. But I think it's a kind of a nice kind of thought experiment to kind of illustrate what the stress stiffening effects look like. Okay. All right. And you can verify this in ANSYS as well. And so, this is a very simple case, but you can definitely set this up in ANSYS and you should get the exact same results. Okay. And so let's consider a simply supported beam. Okay. Right. And so we have a beam that looks like this. Okay. On one end, let's say that we have a pin support. Okay. So that side is pinned to the ground. Now on the other side, let's say that we have a roll, right? And so the right side is kind of free to move left and right. Okay. So let's apply a force on that right side. Okay? And so that force will be, at least in this configuration, it'll be a tensile force. Okay. And so we're pulling and we're stretching the beam to the right. Okay. And then on top, we're going to apply a distributed loading, okay, transverse to the beam. Okay. And so let's apply a distributive force that looks like that. And we'll call this distributed force P. Okay. Right. And so we have F here, which is an axial load, and we have P, which is a transverse load applied to the top. Okay. All right. And so, for all of the data that I'm going to show you, I'm going to assume that P is constant. Okay. And so for all of the data, P is exactly the same. And so the only thing that we're going to change is F. Okay. All right. And what we're interested in seeing is, depending on the value of F, we're interested in seeing what the vertical deflection of this beam is going to be. Okay. Okay. Right. And so notice here I said vertical deflection, right? And so vertical deflection means deflection in this direction. Okay. Okay. And so because we're applying this transverse load P, that's going to cause the beam to deflect vertically, right? And so kind of, intuitively, when you look at the situation, right, and we look at the directions for F and P, which is our loads, right? If we say that P is to remain constant, I think kind of the first intuitive thing that people say is that, because P is constant, our load in that vertical direction is constant, then the vertical deflection should always be constant as well, right? And so, F, changing F, of course, that's going to change the horizontal displacement. But because of the stress stiffening effect, changing the value of F will also affect our vertical deflection as well, okay? Okay. All right, and so remember the stress stiffening effect is, as we change the axial loading on our beam, that's going to change its stiffness or resistance to bending in those directions. Okay. Okay. All right. Any questions on this? Okay. The whole result's going to be summed up in a single graph, but I want to make sure it's big enough, and I don't want to make it drawn on the bottom of this page here. Okay. All right, so let's look at the results of this. Okay. Let's draw a graph here. All right, so on the x-axis we have the magnitude of F, okay, magnitude and direction, and on the y-axis here we're going to have our vertical displacement. Okay, and let's set the 0 point to be around here, okay? Right in the middle. Okay. And so at this point right here, we're applying zero axial loads, okay? And so for values of F that are to the right of this line right here, these are going to be tensile forces, okay? Right. And so those are going to be forces that kind of pull the beam into tension, okay? Whereas on the left right here, we're going to have compressive forces, okay? And so if the value of F is negative, that means we're applying a force that's compressing the beam, okay? All right. And so based on our intuition and knowing that the bending stiffness of the material will go down in compression, what we expect is that, the vertical deflection should be higher on the left side, right? So in compression. And that's exactly what you observe, okay? And so generally the trend will look something like this, okay? Right? And then as we apply increasing tensile forces, with the increasing tensile forces, then the vertical flexion will actually go down because the resistance to bending is going up, okay? And so the trend kind of continues on just like that, okay? And of course, here I'm exaggerating it a little bit just to kind of make the difference more clear, but you do see kind of a pretty significant difference, in between the point of maximum tension versus the point of maximum compression, right? You're going to have actually a lot more, deflection in compressive loading, and that's due to the stress stiffening effect, okay? Okay. All right. And so if you want to recreate this experiment in ANSYS, I do want to note that you have to turn large deflections off, because the stress stiffening effect is one of the many nonlinear effects. Okay. Okay. But it is actually a cool thing to try out. So so this is data that's given in the textbook, but it's something I've tried myself, and you actually see it as well, right? And for someone like me who doesn't really come from a very strong structural mechanics background, so actually seeing this data kind of replicated in practice was actually really interesting to me. Okay. All right. Any questions on this? Okay. All right. And so let's get back to buckling, right? And so what I'm showing you here is the effects of the stress stiffening effect. Okay. But we haven't quite reached the point of buckling, right? So remember, buckling is kind of a very very drastic, kind of very sudden thing, right? And so it's basically when the bending stiffness goes down to 0. Okay. And so in order to see buckling, you kind of have to keep increasing the compressive load, until the deformations get kind of catastrophically really high. Okay. So we have to keep basically going this way. Okay. And the question that often, you might ask yourself is, when do you know if you reach buckling? If you're tracking the data kind of as carefully as the previous one, you'll notice it. Okay. Because, it might look something like this, where, let's say that we have a 0 point just like before. Okay. And let's say that we keep continuing, and then all of a sudden, it's going to jump up kind of like that. Okay. And so the point where it starts to jump up right here, this is the buckling point. Okay. Because basically the bending stiffness of the material got so low that you kind of reached a point where the deformations are going to become more and more exaggerated. Okay. Okay. And so, this is one way that you can perform buckling analysis, right? And so you can have just any kind of structure with compressive loading. And so as long as you turn on large deflections, you can keep increasing the values of the loading until you reach that buckling point. Okay. So it's not that different compared to how we've done our previous activities. Okay. And so it's basically, performing the same kind of failure analysis that we've done, right? And so set up at finite elements, change the load until you reach, buckling. Okay. But it's not the most efficient, right? And so if you're kind of just running simulation after simulation after simulation, trying to find kind of one magic point where buckling occurs, that's, you can do that, but for a lot of people, that's not the best use of your time. Okay. And so, knowing this, ANSYS developed a new module to kind of develop or to kind of determine very quickly, when buckling will occur. And that's what the eigenvalue buckling module is. Okay. Because most of the time, that's what we're interested in. And so we're interested in saying, how much can we load the structure, before it starts to fail, right? And that's what the eigenvalue buckling will tell you. And so eigenvalue buckling will tell you that, you can increase the load by a factor of 4 or a factor of 5, before you actually start to buckle, right? And one way that you can interpret that is you can basically interpret that as your factor of safety, right? And so when you run eigenvalue buckling, and you'll see this later, that it'll display results in terms of a multiplier, right? And so what that multiplier will tell you is that, this is how much you can increase your loads and still avoid buckling, right? And so that's kind of one way that you can interpret that number as a factor of safety. Okay? And the way that ANSYS does this more quickly is that it doesn't actually solve the nonlinear problem, over and over again. And so what it does is it does a special kind of analysis called linear buckling analysis. Okay. And so it basically takes the equations that govern the stress stiffening effect, and it linearizes them. And so in other words, it makes it a lot simpler. And by making this equation linear, then it becomes a lot easier to solve more quickly. Okay. And if you're wondering exactly what it's doing, basically what it's doing is that it's taking the stress tensor at each of the nodes and elements in your mesh, and it finds the eigenvalues of that stress tensor. And then based on those eigenvalues, it'll tell you how much you can actually increase or decrease the load in order to reach buckling. Right? And so we don't have time to go through all the mathematics of that, but that's essentially what it's doing underneath. Okay. All right, and so for the rest of the class today, we'll be going over the eigenvalue buckling module. Basically how to set it up, and what you can expect from it. Okay, and then we'll actually see it in action on Wednesday. Okay, but this is kind of the theoretical background behind buckling, in terms of what you need to know from a theoretical point of view before we jump into ANSYS. All right, any questions on this? Okay, all right, so let's talk about the eigenvalue buckling module. All right, and so before I go forward, I want to give one very big warning about using this linear eigenvalue buckling. Okay, and so because it's a linear buckling analysis, what it tends to do is that it tends to overestimate the buckling loads. Okay? Okay. And unfortunately, that's the kind of bad side to be on, right? Between underestimating and overestimating, because what this will do is this will kind of give you a false sense of security about how much load that your structure can take. Okay. And so what this means is that eigenvalue buckling will tell you one thing, and so it'll tell you that maybe you can increase the loads by a factor of 3 before we see buckling. But in reality, if you actually do the nonlinear analysis, the actual point of buckling might be lower. Maybe it's something like 2.7, 2.8. Okay. And so, with that in mind, it's a very big word of caution. So to not take the eigenvalue buckling analysis at its face value. And so, I'd say it's a good place to start to get you in the right ballpark. But you should definitely check your results against a nonlinear analysis to see if that's really true. Okay, and we'll do that on Wednesday too. Okay, but just know that the eigenvalue buckling will overestimate your buckling needs. Okay. Okay. All right, and so just like I mentioned, okay. The way that eigenvalue buckling will display your results is that it gives you your results in terms of a multiplier. Okay. Okay. And so what that multiplier tells you is that it tells you how much more that you can increase your loads, or in some cases, how much you have to decrease your loads in order to reach the point of buckling. Okay. Okay. And so as an example, let's say that we have a kind of a triangle structure like this. Okay. Okay. So let's say that each of these are beam elements, and so it's kind of a hollow triangle. Okay. So it might look something like this. Okay. Okay. And let's say that we apply a load on top, right? Like this. Okay. And so let's say that P is equal to 2,000 newtons. Okay. Right. And so if you feed this into eigenvalue buckling, eigenvalue buckling will give you a single number. Okay. And so it'll tell you a number, let's say it's 4.20. Okay. All right. And so what that'll tell you is that you can multiply your loads by a factor of 4.2 before you can reach buckling. Okay. And so if you apply this multiplier, in this case, it's a simple case because we only have one load, right? And so we have 2,000 newtons multiplied by 4.2, right? This will tell you that we can apply a load of 8,400, right? Before we can reach buckling. Okay. Right, and so that's how you can basically interpret your results. Okay. And because of the way that eigenvalue buckling displays your results, there are ways that you can set up your simulation to kind of make it more convenient. Okay. And so at its face value, it's not too bad. That's basically all there is to eigenvalue buckling. But there are ways that you can set it up to make viewing the results and calculating the results a bit more convenient. Okay. And so we'll talk about that on the next page. All right, so any questions on this? Okay. All right. And so how do we actually set this up, right? And so before you do any eigenvalue buckling, a requirement is that you run a static structural simulation first. Okay. This is important because this is where eigenvalue buckling is going to obtain things like the mesh, things like your loads, things like your constraints. Okay. Okay. Large deflection doesn't have to be on. And in fact, I think, and on Wednesday, we're going to run it without large deflection. So, you don't have to worry about that. Okay. Okay. And it's not like the modal analysis that we did before Thanksgiving, right? And so if you remember, when we did activity 7, the first thing we did was a static structural as well. But whether or not you use those static structural results in your modal analysis was more or less optional, right? And so it depends on whether or not you want to use pre-stress or not. But for eigenvalue buckling, it is a requirement. So you do actually have to have static structural, because eigenvalue depends on that. Eigenvalue buckling depends on that data in order to run itself. Okay. All right. And so because eigenvalue buckling displays your results in terms of a multiplier, it can be useful to to specify your loads in convenient numbers. Okay. Because a lot of times, as a design engineer, you're, I mean, of course, you're interested in things like factor of safety, but, a lot of times you're actually interested in things like, how much load can actually put on the structure, before it actually buckles, right? And so, it's because of the way, because of this multiplier thing that eigenvalue buckling does, it can be convenient to show results or to specify in a convenient way. Okay. And so what I mean by that is, let's say that we have our same triangle structure from before. Okay, so we have kind of a triangle of beams. And we have a single load that's being applied on the top. Right, so don't make the load something weird, like don't make it like 1,337, right? Right. Because when eigenvalue buckling gives you its number, right? And so if it gives you its number of like 3.6754 something, right? You're going to have to either do a lot of math or use a calculator to to determine what the actual buckling load is, right? Instead, why don't you use a more convenient number? So use something like 100 or maybe 1,000 newtons, right? Because then that's really easy to determine, right? Because let's say that your buckling multiplier was 8.459, okay? But if you're in your static structural, if you apply a load of 1,000, you can very easily say that my buckling load here is going to be 8,459 newtons. Okay. Right. And of course, you don't have to do this, but it is generally a little bit more convenient. Okay. But if you don't mind, putting or punching in numbers in a calculator, then that's fine too. Okay. Because another argument can definitely be made where, let's say that you have a structure and you already know, what all the exact loads are going to be, right? And so, let's say if your loads are determined just on the operating conditions of your structure, right? And what you're interested in finding is, what is the fact under these loading conditions, which are kind of already set, what is the factor of safety, or what kind of factors of safety do I have in terms of buckling loads? Okay, and so that's another way to do it. But if you're interested in determining what the exact buckling load is, doing something like this will be can be a little bit more convenient. Okay. All right. Any questions on this? Okay. All right. And so the next thing I want to go over is the concept of buckling modes. Okay. And so we were introduced to the concept of modes when we did modal analysis before the break. Okay. And so the whole idea with modes is that there are basically different ways that the deformation can happen, or different shapes, right? Okay. And so, we were introduced to this idea when we talked about resonance, right? And so depending on the frequency of the loading that you apply, right, you're going to observe different kinds of deformation, because, that's kind of naturally what the structure likes to do. Okay. And so buckling is the same thing, right? And so there's more than one way for a structure to buckle. Okay. Okay. And the form of the buckling takes will actually depend on the magnitude of the load. Okay. All right. And so as an example, let's say that we have our beam. Okay. And I'm just going to draw it as a straight line, and just like before, we're going to apply a compressive load F on it. Okay. And so depending on the magnitude of F, we can see one of a few different buckling modes. Okay. Right, and so you might have one buckling mode where the bending, the intense bendings takes place in the middle. Okay, so this might be like mode 1. Okay. Right. But say if you increase the force F by a little bit more, you might see another one where kind of the bending takes place kind of near the end. Okay. Okay. And so that might be kind of a different way for the structure to buckle. Okay. And so, in ANSYS, you can view these, right? And so just like we did with modal analysis, you can view all these different buckling modes in ANSYS as well. Okay. Okay. Right, and each of the modes will have its own multiplier. Okay, and so it'll tell you basically, how much more you have to increase the force in order to observe these various modes. Okay. All right. Any questions on this? Okay. All right. One last thing I want to talk about today is a way that you can validate your buckling analysis. Okay. Okay. And so, before Thanksgiving, we talked about how important it is to verify and validate your results whenever you can, right? And so, whenever you can do any kind of outside calculation to check the results of your finite elements, that's always going to be a good thing, because then that increases confidence in your results. Okay. And for buckling, it's relatively easier to do compared to some of the other tools, because most of the times when we're concerned about buckling is, in kind of one kind of unique situation. Okay. And so, most of the time, buckling is going to occur in kind of these thin beam-like elements that sustain compression. Okay. Okay. And a lot of applications kind of take this take this shape, right? And so as an example, let's think of if you think of one of the final project geometries, right? And so if you're working on the two-story building, that two-story building has a lot of beams that are subjected to compressive load, right? And so a lot of times, and I've already spoken with a lot of you, a lot of you are interested in placing kind of a vertical weight loads on the different platforms of the building, okay? And so that's going to put some compressive loadings on your beams, okay? And so, that's a situation where you would be kind of concerned about buckling, right? Because you have a relatively thin structure that's very susceptible to bending. And when you add some compressive loading to it, it's going to make it even more weak to bending, okay? But that's good because, for beams or for slender geometries like that, we actually have a formula that we can use to predict the buckling load, okay? Okay. And so the formula is the following, right? Right. And so the buckling force, for a beam element is given by pi squared times E times I divided by L squared. Where E is our Young's modulus. Okay. I is our moment of inertia. Okay. And that's the moment of inertia of the cross section of the beam cross section. Okay. L is the length of the beam. Okay. And of course, pi is pi. Okay. Right. So pi is 3.14159.257, whatever. Okay. All right. And so this is really useful because if you're performing eigenvalue buckling or any kind of buckling analysis in ANSYS and you get a certain number for the buckling load, you can check your answer against this equation right here, right? And ideally, you should get very similar answers. Okay. And that's one good way that you can check your results. Okay. And so if you get results that are different between ANSYS and between this formula, that's usually a good indicator that you should go back and probably check your results a bit more. Okay. Maybe check your setup, check your boundary conditions, check your loads and constraints, make sure everything's good. Okay. All right. Any final questions on any of this? Okay, all right. So that's all I have to say about buckling. And so, it's a little bit early, but I don't have anything more to say, and I'm not going to stall for another 10 minutes, right? And so I'll let you guys go. And so on Wednesday, we'll do our final ANSYS activity where we'll see a lot of these ideas in practice. Okay. All right. So thank you guys for coming today. I know it's the first day after Thanksgiving, so I know there's a little bit of Thanksgiving hangover. So I appreciate you guys coming out. Right. If you have any questions on your project or anything, I'll stick around for a while. But if not, then have a great evening, and I'll see you on Wednesday. Sure.
My biomechanics project, so like I know that all of this basically start like, okay, well I guess technically the squat would be a little bit harder because you don't pause at the bottom. But of course there is a moment at the bottom when you're reversing where you're pushing from zero, like 0 bar velocity. But like a deadlift starts from flat on the ground, and then a bench you have to pause it on your chest for like a couple seconds or 1 or 2 seconds, and then you're pressing from 0. So I'm wondering, like for my analysis, I do want to include some dynamic analysis, but the thing that I really want to center my project around is like, okay, so for power lift, it's like mainly injury analysis, right? But it's like complicated because it's like, okay, so what goes into injury during powerlifting? A lot of the time, it's not acute injury, it's chronic injury, and what's causing the chronic injury. So what I want to talk about is like a lot of programming, powerlifting programming. Like there's this. Oh, shit.
It's a real act on which areas are working.
So, like there's. So anyway, okay, yeah. So like there's this graph, right? That's like the performance fatigue graph, like this, right?
Yeah.
So like once you get up to a certain amount of fatigue, like your performance is going up, not exactly linearly,
right?
But it's going up, right? So then let's just say this is your maximum fatigue limit, and then after here, your performance like drops dramatically, right? So what most people will do is they'll take something called a deload week. If we have a coach and like they know this stuff, or if you know this type of stuff, right? So what they'll do is they'll take a week to go light here so they can reset their their fatigue rate, right? And then this also ties into how are you programming. So basically what I want to talk about is like, so powerlifting is a sport that, you know, you're developing like absolute maximal strength. So like to get to the elite level, you have to lift for years uninjured. So the main thing I want to talk about is, okay, so how do you keep from being injured? And I think number one is form. Like, so consistent lifting with consistent form over a long period of time, and then sticking to training principles like this and talking about how, okay, if you're constantly going over your fatigue performance peak, then, you know, you're more likely to get injured than if you were to take rest time. And then that also has to do with the fact that your joints are constantly undergoing maximal joint reaction forces because you're constantly trying to go up and up and up and up without taking a break. And then, so that's first what I wanted to talk about. But then second is when we talk about like, okay, what's bad form, right? Like, so for a deadlift, for example, like this would be considered like good form, right? Like a perfectly straight back like this. But then if I wanted to do calculations on bad form, how do I calculate something like that? Like, how can I, like, do I consider this like an eighth of a circle or something? And then how can I get this angle here? And then like, I'm gonna need this distance here. So I'm gonna have to do like a weird arc length like thing here. How am I supposed to do that?
Yeah, so I mean, a lot of that you can take some liberties, like you can definitely make some assumptions to make it a little bit easier for you. I mean, the straight back one, I think is easy. You just make a triangle out of it.
Yeah, it's like what we did in class, pretty much. Like if you were picking something up off the floor.
Right. So for these situations, you can, you know, I think making it like a circle with kind of a large radius, I think is okay. Is there data out there to say, what kind of curvature people would have with that form, or is it just all kind of visual in terms of what people see?
It's definitely visual. Like when you watch somebody who lifts with bad form, no curvature is going to be like exactly the same. I think it's just like, so maybe somebody has tight hips, maybe somebody has weak abs or weak lats. And so like when they start lifting, it will cause their own unique curvature, as opposed to somebody maybe who's like hypermobile at their lower back. Like when they start lifting, maybe the rest of their torso stays straight, but then their lower back like just completely rounds over. So it's like, it's definitely, I can see if I can find some aggregate data out there. But the problem is that like, especially in the US, powerlifting is not really that well researched. Like I've been able to find stuff about like injury rates and how that correlates with years of powerlifting experience. And like, basically, so what I've read is just the higher your total, the less flexible you are generally, because you're probably extremely muscular, if you have like a very high total. And then, maybe you're not stretching as much because generally, like at least up until the last, I would say couple years, like powerlifting, they didn't take stretching seriously. They didn't take warming up seriously. Like that's very much like a new fad. So I think that when I'm looking at the older data, I think that's going to be really apparent. And obviously that's just an assumption that I'm making.
Right.
But like, just from like being in the sport and like around people that lift, that's what I've seen. Basically.
I see. So a lot of the data is more on kind of like not really the biomechanics, but like some of the other stuff that they're doing.
Yeah, basically.
So, okay. So I think maybe one way that you can do it is, one thing I noticed right away from here is that, this part right here, is a lot more straight up. And so you can modify that sort of like, I would assume that when you're like this, that your attachment angle would be kind of, nice and kind of wide. And, generally the larger your attachment angle, the better it's going to be on the back.
Okay.
But when you're arched like this, I think that kind of brings your back kind of closer and more kind of flush with your back muscle. And so I would think that the attachment angle would be much smaller.
Okay.
And so you can do one calculation, maybe you just keep the back straight just in terms of simplicity of the calculation. But for one, you can make the attachment angle bigger for the good form, and for the bad form, you can adjust it to make it smaller. You can see how that changed the calculation. Because that's what I would expect to happen between these two forms. I mean, it's going to be a lot of things, but one of the primary things is, the attachment is going to be smaller.
Okay. Yeah.
And you'll definitely get some results with that as well.
Okay, cool. So I'll do that. And then, yeah, you know, I haven't looked in terms of like the actual biomechanics yet. What I've been looking for so far is like looking for injury rates, and then also looking for like programming type stuff. So like how somebody programs and how that correlates to their increase in like strength results. But I guess what I'm kind of assuming, oh, and then I also found another one, that the one that I was talking about where it said more experienced powerlifters are generally less flexible in the hips and stuff like that. But then they do have increased knee flexibility, something like that.
I see.
And then one was also like the most common powerlifting injuries, which was like elbow, no, shoulder, lower back, knee. Those were the three most common, which I think is like, you know, lower back, deadlifts, knee, squats, shoulder, bench press, and
Makes
probably
sense.
a little bit of squat too, because like they hold it low on their back.
Makes sense.
So I found that, but what I'm so I am gonna look for some more papers on like the actual biomechanics of powerlifting. But basically what I'm assuming is just that when people get these injuries, it's most likely not an acute injury. It's a chronic injury.
Oh, sure.
And even if it is an acute injury, it's most likely from a chronic use of bad form. And then they decided to, you know, go for a PR one day, do a variation on an exercise they've never done, and their chronic bad form basically caused them to get an acute injury. That's how I'm thinking about it.
Yeah, no, I think that makes a lot of sense. And I think that's how a lot of people just generally get hurt with these things too.
Okay. Yeah. Okay. So I just wanted to run that by and like make sure that all made sense.
Oh yeah, no, that makes perfect sense. And that's kind of what I expect from this.
Okay. And then so I'll just, because the deadlift is my favorite lift. And I also think that just like based on the stuff that we've been doing in class, like this will be the most understandable for people.
Oh yeah, yeah.
And then in terms of like, because the instructions said like, oh, you know, why is this important when compared to the class? So like, how should I be writing the paper? Should I be writing it with no personal pronouns whatsoever? Because like when you did the instructions, you're kind of making it seem like, okay, how do I want to relate it to what I learned in the class? So should I be writing it?
You can use some personal pronouns.
Okay.
I think that's fine.
Okay.
Especially if you have like personal experience with these stuff. Like I think that's important to know too.
Okay.
But specifically what I meant for that is how can you relate it to kind of the other stuff that we talked about in the class?
Okay.
Like I would say like all the first half stuff. So everything on the first midterm, we talked about like bones in general, muscles in general, joints in general. Like how is this, you know, how does this relate to kind of that stuff as well? And so I want you to incorporate kind of as much of the information we learned in the class into the report as possible.
Okay.
So it's
So
kind of a synthesis of like what we learned in the class and also what you're also researching independently as well.
Okay, so definitely, I feel like the injury mechanics ties into that. Like, you know, you could injure tendons, muscles, joints, and a lot of the time that does happen. Those catastrophic injuries are rare, though. I would say, but I think like, you know, because people do tear their pecs and stuff sometimes. I've even seen quads, and I saw a lot, but that's like really rare, you know. And it's like the reason I hear about that stuff is because like when it happens, everybody's reposting it. So like when I'm going on my Instagram, like there was a guy, because I was, so remember when I was talking to you like a couple weeks ago in class, and I was talking about how like your lats like help to keep this part of your back rigid. So it's like, so there was a guy who was doing that in a powerlifting competition, and his whole lat tore off of his arm. And it was just, and everybody was just like, holy shit, I've never seen that happen before. Like this is like the first time I've ever seen that in all my years in the sport. So it's like stuff like that does happen, but it's rare.
Yeah.
Because even in this case, like his form was good. And like he was doing everything he should have, but it was just a case where like his muscle just got completely overloaded.
Yeah. But then those get shared the most. And so, it makes it seem like it happens more than it does.
Exactly. But I would say it's more chronic. So I could talk about that, how that relates to muscles, joints, ligaments, and tendons.
Yeah.
Should I also do like a section saying like, okay, when powerlifting is performed correctly, it can help increase bone density, joint stability, all that type of stuff.
Especially if you find research papers that back that up with data, absolutely. Okay, that'd be really cool.
Okay, yeah, I would say that I might be able to find more bone density stuff about weightlifting, I
Yeah.
think, just because I've seen some stuff like that.
You can
But
apply
I
that
would
stuff
say
too.
it's from squatting, which powerlifters also do.
Oh, yeah.
Because I saw some stuff that was like, there was a big correlation between doing a lot of heavy squatting and higher bone density.
Mhm.
And it's probably because like, you're just like, you're standing with it.
Yeah.
I
You're
feel like-
just putting more weight on bones.
Yeah.
Yeah.
And
that makes perfect.
I feel like something like a deadlift where you're like just picking it up off the floor.
Mhm.
I mean, I don't really see how that would increase your bone density all too much.
It should help. I mean,
And like a bench, like, maybe you have super thick forearms or something.
Yeah, yeah.
But like,
I mean, anything extra that you're doing besides just, standing around like a couch potato, I think is always gonna have to be.
Okay.
So, yeah, any kind of general like weightlifting data that you can find on that, I think absolutely you can apply to.
Okay. And then, so when I say like, in my intro, like, oh, how is this relevant to the class? I was thinking about saying something about how like powerlifting is, it's basically a controlled environment with very specific standards. And like the weights are totally uniform.
Yeah.
And they're easy to lift. Like it's
Yeah.
not like a rock or something. Like
Yeah.
it's a bar with a uniform diameter, plates with a uniform diameter.
Yeah.
Everybody's lifting from the same height.
Yeah.
So you get a really good idea about the biomechanical, I don't know, the biomechanical activity that's going on during the lift. Like you have a
Absolutely.
really clear picture of joint angles,
Mhm.
muscle forces, and all that type of stuff.
Yep.
And then how that differs from individual to individual.
Yeah, that's exactly what I was saying. And
Okay.
if you notice, like a lot of the examples we do in the class is from like weightlifting or
Yeah,
powerlifting stuff. I think,
Totally.
because it's so easy to quantify, because it's
Yeah.
a very strict motion. The object itself is really simple to lift. Like there's no kind of weirdness or awkwardness to it.
Yeah.
And so I think it lends itself really well to the class, just really naturally. So yeah, I think all that makes a lot of sense.
Okay, cool. Alrighty, yeah, so I think I'll do my presentation on the deadlift.
Mhm.
And then if I feel like that's not gonna be long enough,
Mhm.
do you think that I should maybe add in the squat or the bench press? Or should I talk about like because I want to talk about the, like, especially like the programming and then the stress, and then the fatigue performance chart, because I feel like that ties in really well when it comes to like the injury mechanics. But then after that, if that's not enough, should I also add in like a squat or a bench press? Or do you think I should talk about like, oh, here are the health benefits of powerlifting and blah, 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 increased bone strength, increased muscle strength, aesthetics, health, all that stuff.
I would prefer to just focus on just the deadlift, and then you can incorporate all the other stuff too.
Okay.
And so yeah, I think that would be a good direction. But I also say that the 15 minutes is an absolute maximum. And so
Okay.
because we have such a fairly high number of presentations.
Okay.
If you're short of 15 minutes, I'm not going to mark you down on it.
Okay.
If it's only like 5 minutes and it's clear that you didn't prepare anything,
Yeah.
that's when I start to mark people down. But if you're only like 10 minutes or 12 minutes, like that's a lot of content already.
Okay.
And that's that's fine.
Okay.
So usually the problem that I have is that people actually want to fill in space, and so they kind of just keep talking. Or I think in a lot of cases they just don't prepare and they just kind of just load it up on a bunch of slides.
Yeah.
That's when I start marking people down. So they go like
Okay.
20 minutes, 25 minutes, sometimes like 30 minutes.
Jesus.
And then so obviously you weren't prepared for this, but
Yeah.
if it's between like 10 and 15, I think that's perfect. So you don't feel like you have to fill in the space.
Okay. Cool. Sounds great. Alrighty. Thanks, Professor.
Yep.
I think I'm gonna do some controls. What?